We are given f of x equals negative 1/5 times the quantity x plus 3 times the square of x plus 1 times the square of x minus 2. We want to determine the degree, the end behavior, determine whether the degree is odd or even, the y-intercept, the number of turning points, as well as the zeros and their multiplicity. Let's begin by determining the zeros. These are the x values for which the function value equals 0. We'll notice the right side would be 0 when x plus 3 equals 0, which would be when x equals negative 3. X equals negative 3 is a 0, and the 0 has multiplicity 1 because there's one factor of x plus 3. X plus 1 equals 0 when x equals negative 1. X equals negative 1 is a 0 because we have two factors of x plus 1. The multiplicity is 2. And then finally, x minus 2 is 0 when x equals 2. X equals 2 is a 0 because we have two factors of x minus 2. The multiplicity is 2. The zeros also give us x-intercepts. We have x-intercepts at negative 3, 0, negative 1, 0, and 2, 0. Let's plot these on the coordinate plane. Notice the sum of the multiplicities is 1 plus 2 plus 2, which is 5. This indicates the polynomial is degree 5. And for part D, 5 is odd. Another way to determine the degree would be to think about expanding the function rule. And because we have a degree 1 times a degree 2 times a degree 2 polynomial, we would have a degree 5 polynomial. And also notice the leading coefficient would be negative 1/5. So if we expanded f of x, we would have f of x equals negative 1/5 times x to the 5th, and then plus several additional terms. But just by knowing the leading term, we can determine the end behavior of the given function. Again, because we have an odd degree polynomial and the leading coefficient is negative, the graph goes up to the left and down to the right. Let's go ahead and label this on our graph. Again, because we have an odd degree polynomial and the leading coefficient is negative, the graph goes up to the left and down to the right. Which means with the left-hand end behavior, as x approaches negative infinity, the function values increase without bound and y approaches infinity. And for the right-hand behavior, as x approaches positive infinity, the graph goes down, and therefore the y values or function values are approaching negative infinity. And now to determine the y-intercept. This is where the graph intersects the y-axis. For every point on the y-axis, x equals 0, which means to determine the y-intercept, we determine f of 0. f of 0 is equal to negative 1/5 times 0 plus 3, or 3, times the square of 0 plus 1, or the square of 1, times the square of 0 minus 2, or the square of negative 2, which equals negative 1/5 times 3 times 1 times 4, which is negative 12/5. The y-intercept is the point 0, negative 12/5, or if we want negative 2.4, which should be approximately here. And now for the last part of the question, they want us to determine the number of turns the polynomial has. A degree n polynomial can have at most n minus 1 turns, which means we can have at most 4 turns. And a turn is where a function changes from increasing to decreasing, or decreasing to increasing. Let's make a rough sketch of the polynomial function, and then we'll check it on the calculator to determine the number of turns. Recall, if the multiplicity of the 0 is 1, the graph must cut through the x-axis at that point. And if the multiplicity is 2, the graph is tangent to the x-axis at that point, or it touches the x-axis and bounces back. So sketching the graph from left to right, the 0 of negative 3 has multiplicity 1, and therefore the graph must cross through the x-axis at that point here. At some point, the graph has to turn so that we can reach the next x-intercept of negative 1, 0. Because the 0 of negative 1 has multiplicity 2, once the graph touches the x-axis, it's going to bounce back. Then it has to pass through the y-intercept. And then it has to turn again to reach the next x-intercept of 2, 0, which once again has multiplicity 2, and therefore it's going to touch the x-axis and then bounce back, and then we know the graph goes down. Analyzing the graph, the function is decreasing, increasing, decreasing, increasing and decreasing. We have 1, 2, 3, 4 turning points. So this polynomial function does have the most possible turning points for a degree 5 polynomial function, which is 4. Graphing the polynomial with technology, the actual graph of the function verifies our work. I hope you found this helpful.